Hello, everyone, and welcome to Lesson 2 of Physics. Today we're going to be talking about relative motion. Now, I will say that this week and the last week are not the hardest topics. Definitely the hardest stuff is yet to come, especially with week 3, which is going to be kinematics. But until then, we're going to be talking about relative motion, which is basically things moving in relation to other things. Let me give you a quick example. If you are, for instance, moving in a car, what happens when you jump out of the moving car? And let me tell you why, like obviously it's going to hurt, but let's talk about why it hurts. Because when you're in the car, do you feel like you're going 50 miles an hour, 60 miles an hour? No, you don't. You feel like you're going like not at all. It feels like you're just sitting down in like a chair. But as soon as you jump out of the car, like let's say this car, it's a New Jersey car, so it's going 70 miles an hour, and that's a slow car, and then you jump out. Well, is your speed 0, 70, or something in between? Let's say you jump out, like you just fall off the car. You fall out of the car. In other words, you're not inputting any speed yourself. The answer is you are going 70 miles an hour, just like the car. And so that's why it hurts. It hurts when you hit the ground, not because you're not moving, precisely the opposite. You're moving the same speed as the car. And what we're going to be talking about today is there's different reference speeds. In other words, let's say your little brother is sitting in the car next to you. He's going to say your speed is 0. But someone on the side of the road, like a hitchhiker, is going to say you're going 70 miles an hour. So that's what we're talking about today. Now, problem 1. A plane is moving at 200 miles per hour, drops a package to the people below. The plane drops the package directly above the people. Is this a good idea? So basically, there's one of two outcomes here. Outcome number 1, I suppose the plane drops the package right on top of the people, which would not be good. Or, in the very least, we'll say next to them. They can get out of the way. The plane's moving 200 miles per hour that way. And of course, I think you see what I'm alluding to here. Is the package going to drop straight down so the people catch it?
Oh, I don't think so because the package itself is also moving at 200 miles.
Yes, exactly. So since the package is 200 miles per hour, that means it's going to not hit them at all. As a matter of fact, what we would say is it follows a trajectory that looks something like this. We call that a projectile motion kind of diagram. But we're not going to focus on that until next week. And after next week's lesson, you'll be able to tell exactly how much it overshoots by. You can actually solve for that distance d. But is this a good idea? No. The package will go too far. We'll say it will go past the people. Problem 2. You are in the back seat of a car that is moving at a constant speed of 40 miles per hour, just like the last example, basically. You pass an avid bicyclist who is going 15 miles per hour in the opposite direction. So I know I didn't give a lot of room here, but let me just draw a picture of what's going on. You've got a car, you're in the car is going 40 miles an hour that way. You pass a bicyclist. Now, if you really want to see how bad I am at drawing, you should watch how I draw bicycles. Okay, there we go, beautiful. And that bicycle is going 15 miles per hour in the opposite direction. Now let's go back to the questions. Assuming you're riding in a 2020 Kia Forte, very smooth ride, how fast do you feel like you're going? Well, basically, if you don't feel like you're jostling around like it's very smooth, and you, for instance, close your eyes, you shouldn't be able to tell if you're going 40, 10, 100, because it feels like you're going 0. It feels like 0. Okay, that's the answer to the first part. Now, part B, what is your speed from the perspective of someone on the road? So, someone on the road, they're just going to see a car going at 40 miles an hour. So, they see 40 miles an hour. And then finally, part C, this is the real question. This is where you have to use your brain for a second. What is your speed from the perspective of the bicyclist? Here's my advice to you. Whenever you have two objects coming towards each other, whenever it's towards each other, then you're going to add the speeds. And I know it's not away from each other, but if they're ever heading not so much towards each other, but or not away from each other, but like I'm trying to say the same direction. If they're going in the same direction, like both forwards, both backwards, then that's when you would subtract the speeds, which is not this example. So in other words, if you want to know the bicyclist, you're just going to take the speed of the car, 40, and add the speed of the bicyclist, 15, because they're heading towards each other. And so the final speed that the bicyclist sees is 55 miles per hour. Now here's a fun question for everyone here, and you can think about this too for those watching the recording. When you're let me just draw a picture. This is a bird's eye view, okay, of a road, and here's the line going down the middle. And let's say, cars, if I'm drawing this right, cars go that way, and another car, they go that way, right? That's just how roads work. My question is, if you're walking and you're walking north, so that way, you're a person, you're walking north, should you walk on the same side of the cars or against traffic, against the cars? And so now what you're thinking is probably something like this. If you have a car going, let's say 40 miles an hour, and we'll say both of these cars is going 40 miles an hour, and you're walking, let's say you walk with a speed of 2 miles per hour, you don't walk that fast. Well, then, if you're walking this way, right, if you're walking this way 2 miles per hour on this side of the road, then what's the car going to be looking like? It's going to look like 42 miles per hour, isn't it? And it will. The left side, 42 miles per hour. In other words, slightly faster. Then on the other side, same scenario, 2 miles per hour. You subtract because they're going in the same direction. So you're seeing 38 miles per hour. So which way should you walk? There's two theories here. One theory is, well, it's slower on the right, so walk on the right. My theory is, and this is the right answer, if you get hit by either of these cars, you're dead either way, or at least severely injured. So in other words, I would rather walk on the left because then I can see the car coming. And that's why this is like an actual practical piece of life advice. Walk against traffic. Walk so you see the cars coming towards you so you can get out of the way if you see it coming towards you. If it's coming from behind you, you're gone. You're a goner. And that's a fun real life example. Now it's different if you're on a bike. If you're on a bike, you're probably going like, let's say 15 miles per hour, 20 miles an hour. Now you're actually going at a reasonable speed where you can actually save yourself if you get hit. And it would actually be crazy dangerous to go against traffic. So that's a fun example, if you call that fun. Number three, you are walking. Oh, this is crazy. This is the craziest example you ever see with relative motion. You are walking 2 meters per second north on a train that is moving 20 meters per second south. The train is on a cruise ship that is moving 32 meters per second north. You pass a buoy floating motionlessly in the water. What is your speed as seen from the buoy? So one thing I want to tell you, everything I just said with the towards each other, away from each other, it only works if the ground is not moving. What do I mean by that? In the last example, was the road moving? No, of course not. The road's not moving. But this time your ground is moving because you got walking north on a train that's heading south on a cruise ship that's heading north. So whenever the ground's moving, what do? We need to add these vectors together. And I'm going to show you how we do that. It's going to be similar to what we did in week one. So first, if you're walking north 2 meters per second, it's going to look like that, 2 meters per second. Then we're going to add to that a 20 going south, like that. And then from there, you're going to add another one going 32 meters per second north. If I want to add these all together, we typically in physics consider north to be positive and south to be negative. So in other words, I'm saying 2 minus 20 plus 32, that's our net speed, our total speed. So that's minus 18 plus 32. You're going to get 14 meters per second. And that's going to be your speed seen from the buoy, which is not moving in the water. Any questions on that one? Okay then. Part B. What is your speed as seen from someone sunbathing on the cruise ship? So in other words, they are on the cruise ship. They cannot tell that you are moving the 32 meters per second north, like the buoy does, because they're on the cruise ship. Basically, what I'm trying to say is if they're on the cruise ship and that's your perspective, remove the cruise ship vector. Remove the cruise ship vector. Remember, that was the 32 meters per second north. So in other words, they see someone going 2 meters per second north minus 20 meters per second south, and I don't even include the 32. So 2 minus 20 is negative 18. But see how they ask for speed? Remember that speed is the absolute value of velocity. So in other words, it's not negative 18, it's positive 18 meters per second for the speed. And that is true whenever you see the word speed or whenever you would see the word magnitude. That's another keyword that says ignore the negative, take the absolute value. Any questions on any of those? Okay. And now we basically hit the halfway point already. This is going to be a pretty short lesson. But as you can see, we are now on to river physics. And of course, that has an exclamation point because this is an exciting topic for me. This is actually the very first topic in physics I learned, not from class, but from my friend who took this class before me. And he showed me some physics, and he was showing me river physics. So naturally, this is the most exciting part of the year, at least for me, because I get to reminisce. So, number 4. Oh, before we get started, actually, I want to talk about river physics. Basically, here's what we're going to use. We're going to use the formula velocity equals a distance over time. Or if you'd like to see the abbreviation for this, you would say velocity equals d over t. Keep in mind, the only time you get to use this, the only time you get to use these equations is if you have no acceleration. That's an n. It's a terrible n. You can only do this if you have no acceleration or constant velocity. If you see the words no acceleration or constant velocity, then you are allowed to use this equation. Now, going back to the question, number 4, you are in a boat that can travel at a max speed of 10 miles per hour in calm waters. We're going to assume that's a constant speed of 10 miles per hour. You're not changing. You are heading upstream to a town that is 8 miles away. The river has a current that is moving 6 miles per hour in the opposite direction. Part A, what is your speed as seen from someone standing on shore? Let me draw a picture of this scenario. So here's our river. Here's our boat. It's angled that way, which means it's going that way. We're going to say the boat is going 10 miles per hour upstream, that way. We also know the river has a current that's going to point 6 miles per hour in the opposite direction. And we know there's a town, let's say 8 miles away, because that's what the question says. So the first question we need to answer is, what is the speed as seen from someone standing on the shore? This is another one of those where your road is moving. What do you do when the road is moving? Add the vectors. Add the vectors. So you got 10 to the right, so it's positive 10, minus 6 to the left. Your speed, or velocity, is positive 4 meters per, not meters per second, 4 miles per hour. Any questions on that first one? Okay, great. Part B, what is your speed as seen from someone floating in the water? So remember, if they're on, the last example, they were on the cruise ship. In this example, they're floating in the water. If they're floating in the water, you need to remove the water vector because they also are in the water. So what that means is the answer is just 10, and it's literally just 10. You removed the 6 miles per hour. And the other thing worth mentioning is that for someone floating in the water, to them, it looks like the boat's going 10 miles per hour. But you and I both know if we're standing on land, it's actually only moving 4 miles per hour in reality, which is pretty interesting. And then finally, part C, how long will it take you to reach the town? So notice the town is 8 miles away. We want to solve for a time. So that means we're going to use the equation velocity equals distance over time. Now the trick here is realizing which velocity we need. We're either going to use the 10 miles per hour or the 4 miles per hour. I'm going to tell you, we need actually, I don't want to tell you. Any guesses?
4 miles per hour?
4 miles per hour is correct because I am looking at it from the perspective of someone on land. Because why? Because the town is 8 miles away on land that's not in the water. It's not floating down the river. That'd be horrible. So yes, it is 4 miles per hour is the velocity, equals the distance, which is 8, divided by the time t. Now, whenever you want to solve for t and get it out of the denominator, there's only one way to do that. You need to multiply both sides by t to get it out of the denominator. That means we're looking at 4t equals 8, and then you divide by 4, so t equals 2, and the units are hours because we're looking at miles per hour. Any questions there? Okay, then good. Number 5 is going to be the beginning of where you start crying, but that's okay because I have tissues. I always have tissues. Number 5, a boat is trying to move 4 meters per second straight across a river, but the river has a current of 3 meters per second. So what's going to happen in real life? In real life, the boat's not going to go straight across. Oh no. It's actually going to go down at a diagonal. So that's a problem, potentially, if you don't want to do that. But now we're going to figure out the physics involved here. So part A, what is the speed of the boat from the perspective of someone floating in the river? Again, if they're in the river, I need to do what? I need to remove the river current vector. Remove current vector for the current in the water. And so what that means is the only vector left is 4 meters per second going up towards the other side. So what speed do they see? They see 4 meters per second. Easy. And now here's the hard part. Well, there's also a backside to this on the next page, so you're not out of the woods yet. But part B, what is the speed of the boat from the perspective of someone standing on the shore? This one we cannot ignore the 3. You have to add them together. The bad news is you can't add these like 4 plus 3 is 7. You can't. Why not? Because remember what we learned in week 1. You can only add vectors if they point in the same direction, like x or y. So what do? Because these don't point in the same direction, what do? You construct a right triangle. We're going to make a right triangle, and we're either going to use Pythagorean theorem or SOHCAHTOA. We'll see. So one vector going up 4, one vector going to the right 3, and you'll see the hypotenuse is what we want, which I'm going to call C. This is a right triangle, because I said so, and it's a right angle. And so now we see it is Pythagorean theorem, which means C squared equals 4 squared plus 3 squared. How would I know if we needed SOHCAHTOA? I would need SOHCAHTOA if I was solving for this angle here, like theta. But we don't need that, so it doesn't matter. So that
Oh,
means,
and
go ahead.
we know the answer because it's a Pythagorean triple.
That is exactly right. In other words, this is a 3, 4, excuse me. There's a 3, 4, 5 right triangle. And in case you don't see that, 4 squared is 16, plus 3 squared is 9, c squared equals 25, and you take the square root, and c equals 5. And so that's the speed from someone that someone sees on shore, 5 meters per second. Now you will notice there is a backside. There's a part C and D. Let's see what those parts say. Part C, how long does it take to cross the river? Okay, let me just draw this again so I have it on this page. So again, we know the boat is heading that way at 4 meters per second. We know the current is downstream 3 meters per second, and we know the entire thing is 40 meters long. If you want to get to the other side of the river, you're not looking at the 5 miles per hour we just found in the last part. Why not? Because that 5 miles per hour was along the diagonal. I don't care about the diagonal. I just want to cross the river. Which dimension's that? It's the y component, the 40 meters. So in other words, I'm going to be using v equals d over t again. Velocity equals distance over time. The velocity is the 4 only. Why? Because that's the only component going north, is the 4 across the river. So 4 equals the distance, which is 40, divided by time, which is what I'm solving for. Same thing as before. Multiply both sides by t. 4t equals 40. And then you divide by 4. T equals 10. And the units this time is seconds, because it was in meters per second. And now I'm sure the question we've all been waiting for, or if not, then I'll just ask it anyway. How far did the boat drift down the river? Because that's a problem. So let's call it this distance right here. Let's call it x. We're solving for x. First of all, it's a distance, so I'm probably going to use v equals d over t again. But I want you to notice that we need to think carefully about our velocity and our time. So first of all, our velocity this time, it's not the 4 because that's going across the river. It is the 3 because that's the component going to the right, just the x component. And again, it's not the 5 because that's the diagonal. I don't care about the diagonal. I just want the x distance only. That means I'm only looking at the 3 because it's the only one that points in the x direction. So 3 is the velocity equals distance, which is what I'm solving for because that's going to be how far the boat drifts down the river. And then the time. Will the time be longer, shorter, or equal to 10 seconds? Any ideas?
It would be equal
I
to
think it
10
will be the 10
seconds.
seconds.
Thank you, both of you. So yes, it is equal to 10 seconds because that time is the same. So then we multiply both sides by 10, 30 equals d, and that's how far you go downstream, 30 meters. Is that a problem? Probably, because you're going pretty far downstream. And that's why problem 6 exists. Problem 6, we correct the problem from number 5. Number 6, if we want to go straight across the river, what angle should we steer the boat? So I'm not going to lie, I've had a lot of students try this one. I've never seen anyone get it, but I feel like I explained the first 5 questions pretty well, so I have high hopes that one of you guys can figure it out. And if you're in the recording, think about that too. But does anyone in the live class, does anyone know the answer of how I'm
Yeah,
going to solve this?
yeah, I think I kind of understand it. So, we make a right triangle. 6 would be our hypotenuse. 2 would be one of our legs,
Now hold
and
on, why
then
is 2 one of the legs? I'm assuming you're saying this one.
yes,
Why?
because it's we're adding the vectors, like, and but just like in the other problem where we formed the right triangle,
Yep,
it's basically the same thing. And then
you
we
are
use
right.
oh, okay, and
You
then
are
we use
right.
okay, then we use the Pythagorean theorem to find the other leg, which
Oh,
would
that's
be
not the question.
oh wait, no, we don't need that.
Let me
Oh, okay.
explain.
Oh,
We
I'm
would
gonna
use.
then we could use cosine to arc cosine something.
thank you for your input, but I'm the one running these classes, and people
Mm,
pay good money for these free classes. So I'm gonna take over for here. But thank you very much. You are very close to being right, and you were thinking. I can tell where you were going with that. So I'm gonna say you were very very close. So first, I want to address the question: why is 2 in this leg? It's because if you want to go straight across, then you obviously have the 2 meters per second going to the right, which means you need a 2 meters per second going to the left to cancel it out. That's basically the theory. Or you can also say you can add the vectors together and you get straight across. That works too. Now, the other thing is this last component here, y, we don't care about that because we're solving for theta, the angle. Now, one thing you were wrong about, unnamed student, to keep your anonymity, just like a secret identity for a superhero. One thing you were wrong about is that this is actually the opposite leg, 2, and 6 is the hypotenuse. So I'll give you a chance to redeem yourself.
oh, that would be sine, right?
It is sine. So sine theta equals opposite 2 over hypotenuse 6. Then we use the inverse sine of 2 over 6. You just need to plug that into calculator. Make sure your calculator is in degrees for this, and you'll get 19.5 degrees. And there you go. And now you've steered straight across the river. Now, what's funny is in real life, you wouldn't have to actually do this calculation. Even a complete idiot would know how to steer the boat straight across because as soon as they see they're going downriver, they would just steer more. And if they oversteered, then they would turn it back and go more forward. And the reason why you don't need to actually know physics in real life is because the only time you'd have to really know for sure is if, let's say, this was a remote control boat, and once you set it on its course, it couldn't change course. Of course, robots don't even work like that in real life because robots are something called a control system, which is something I studied extensively as an electrical engineering in college. But to give you a very long semester worth of input down to a single sentence, basically, humans and machines, we can act with response systems, feedback systems. In other words, when you see you're off the mark, you can change your mark. In the same way, if you notice that you're running late to school, you can get to school faster. You can wake up earlier. And the same is true for these boat examples. So, anyways, The goal of this problem is to understand how to solve complex problems, because then if you can solve complex problems, then your skill set in the marketplace is going to make you very valuable to any employer who wants to hire you. And another thing, this is just the common expression, why do I have to learn this? It's because basically every other, let's say you want to be a mechanical engineer, let's just say hypothetically. Every single mechanical engineer who graduates from any university is going to know how to do this because they've done it before. Maybe they don't know it when they're hired, maybe they never use it. But if I'm someone who's hiring for mechanical engineers and I come across your resume and I see you didn't pass physics 1, I'm not going to have much faith in you as a physics engineer, or even not physics engineer, just a mechanical engineer, because you couldn't even do the most basic course. How are you supposed to get to the harder courses? That's kind of the theory. So a lot of it is a test, and the test is, are you able to understand complex topics so that you can then understand more complex topics? Because believe me, I was an engineer in the real world too at one point, and it is not super straightforward. Believe me, there are some complex problems out there. But the secret is never giving up and be willing to try and learn new things. If you have that attitude, you're going to succeed in whatever you do in life. That's a promise. Now, part B. After we choose the correct angle, what is our speed as seen from someone on the shore? So, what does someone on the shore see? Someone on the shore just sees a boat going straight across. In other words, we need to solve for the y component now. The cool thing is you actually have three ways of solving for the y component. One is Pythagorean theorem, one is cosine theta, because you know what theta is now, and the third is tangent theta. No one wants to do cosine or tangent, I'm pretty sure. Everyone wants to do Pythagorean theorem, so we'll do Pythagorean theorem. 6 squared equals 2 squared plus y squared. That means 36 equals 4 plus y squared. Subtract 4. 32 equals y squared. And then y is just going to equal 5.7 meters per second. Any questions on that one? Okay. And now for the last problem of the night. I will say there is a homework problem based on number 7, except if I remember correctly, there's an extra step than what we're doing right now. So basically with number 7, we want to go east across the river as fast as possible. It doesn't matter if we end downstream. Our boat has a maximum speed of 10 meters per second, and the river has a current of 5 meters per second south. Should we go straight across the river or at an angle? And this is a great question, again, if you want to be a problem solver in any field that you grew up doing, okay? Because basically our problem is we want to get across the river. The constraint is you want to go across the river as fast as possible. Now you have two boats, essentially. One boat you can take at an angle, 10 miles per hour, but it's at some angle, so you're going straight across. Yippee. The other boat is going to try going straight across. It's going to aim, I shouldn't draw the dots there, sorry. It's going to try and go straight across 10 miles per hour, like that. But as you soon find out, it's actually going downstream like that. So my question to you guys, and including those of you at home, is which boat is going to get to the other side faster? Do we have any guesses?
The one that's going 10 miles at an angle.
Okay, we have one vote for angle. Any other votes?
I agree with the one with the angle.
Okay, we have 2 votes for at an angle. Now, how are we going to prove it? Oh, I forgot to draw the river speed. So the river is going south 5 meters per second. Now, here's the first thing I want you to focus on. Remember, in physics, you have an x and y component, right? In this example, the river going across is the x component, or at least the way I drew it, right? I mean, in the problem, it said east, so I followed the picture. So what I'm trying to say is to get across the river, we only focus on the x direction. So that's good for us in terms of doing as little work as possible, at least for the one going straight across, right? Because the one going straight across, we already have the x component, it's 10 miles per hour. It's annoying because now we have to figure out the x direction for the angle one, but that's okay, because we already know how. We just talked about it already in the last problem. For the one going at an angle, all you need to do is set up a triangle where the hypotenuse is 10 and you add to that the river current, which is 5, right there, and then you're solving for x. Now again, I'm not solving for an angle theta. I could if I wanted to. I don't really care, frankly. But now, if I want to find this, all I need to do is Pythagorean theorem. 10 squared equals 5 squared plus x squared. 100 equals 25 plus x squared. So then 75 equals x squared, and x is going to be the square root of 75, which is 8.66 miles per hour. So again, that's if you want to go at an angle. Now let's do the same thing for straight across. We are going to make a right triangle for straight across, but you're going to see this one's different. For the straight across one, the 10 miles per hour is not the hypotenuse. It's just to the right. 5 meters per or miles per hour going down like that, and the hypotenuse turns out to be a vector right there down at the angle. And since I only care about the x direction, 10 miles per hour, it's just 10. So in other words, who wins the race? Who's going across the fastest? Straight across. Now, of course, there's trade-offs in life. So first I'm going to write the answer. Straight across is faster, because it is, because the speed, 10 miles per hour, is faster than 8.66 miles per hour, slower. But there's trade-offs in life, right? So the trade-off is, yes, you got to cross the river faster, but now you're more downstream. And if the goal was, let's say, to get to the same point, the finish line, like right there, well, now after you get your boat to the end, you got to like run your way back to that point. And that's actually what you're going to be doing. And I think one of the homework problems, if I remember correctly, it's like a boat race just like this, except the one going downstream has the added leg of the race. They need to run to the finish line. And I'm not going to tell you which one's faster. You'll tell me. Okay? So I know today was a short lesson. It's because, honestly, this was, again, theoretically one of the easier lessons. I know this was not easy because there's a lot of SOHCAHTOA, a lot of Pythagorean theorem, a lot of adding vectors at angles, and that's never easy. But I will tell you this. This is technically speaking the easier part of the year. We're going to be looking at a lot of equations next week. So I hope you brought your pen and pencil. I hope you bring it every week. But I hope you write everything down next week because we are going to be memorizing like 5 to 7 different equations. So I know it's going to be a lot, but it's the most important stuff of the year. Why? Because everything we're doing is basically going to cover at least the first half of the year, at least the first half. I'm not sure what your high school does in terms of the pace, but at least when I was in high school, I'm basically going to tell you we're going to cover up to February, at least. We're going to cover up to February at least. So that's pretty good. So if you have any questions, stick around for the end. If not, you're free to go. Thank you all for watching, and I will see you next week. Bye-bye.